students. With the previous lecture, we are done video lecture. We are done with the transform analysis part. And from this video lecture onwards, we will be starting our discussion on sampling. So this is a very important topic in signal processing. You know that there are two signals, continuous time and discrete time signals. Most of the times sampling becomes essential because when you are doing a discrete time processing of most of the continuous time signals, you need to take samples of it. So one should have a basic idea of how many samples are good enough, right? And suppose when you are taking samples of a given signal, how the frequency spectrum is varying. You again assume that, see, for example, starting with this sounds audio signal, which is originally a continuous time signal. For all your processing and everything, you will be taking, even now the mic will be capturing at a particular takes it at a particular rate. It takes samples of it and then processes it. So you could do it at different rate of samples. So this is something which gives you the understand, gives you the basis or fundamentals, foundations required to understand in the first place how many samples would be, for example, at what rate you need to sample it out, okay? And then how the frequency spectrum varies. So how could you do a discrete time processing of a continuous time signal? After you are done with that processing in the discrete time domain, how to convert that into the continuous time domain? And in theory also, can we tell you certain limits that it's good enough if you take so many samples for a given signal, such that you will be able to reconstruct very well whichever is there in the continuous time domain. So these are all different aspects that we would be discussing, or rather this is the course that lays you the foundation for that. And again, see, there could be two scenarios you could think of. One is signal being continuous time signal, and then you want to do a discrete time signal processing. For example, as I already mentioned, this audio signal or the images that we are capturing, okay, these are all discretized versions of a continuous time signal, right? And there could be some things could be discrete in the nature itself, in its nature itself. For example, you want to look at how the stock markets are varying or each day, okay, that's a discrete time signal. Or now that the corona is prevalent, number of cases on a given day that you are having, new cases that you are having for corona. Or on a positive side, the number of cases that have been treated per day in corona with any given disease. So those are discrete time signals already. Even when you have the original signal itself being discrete time signal, even then also this understanding sampling becomes very important, because you would be later, you for various purposes you may want to either downsample or upsample the image. At that time you require the understanding of how sampling works, how frequency spectrum changes, and all other things, okay? This discussion of this chapter would give you the foundation required to make a detailed analysis in later parts, okay? So for this purpose, what I did is, this is what, what I plan to do is, this would be, I plan to divide the whole lectures into 7 lectures in sampling. So this is the idea to begin with. Maybe I will change your time slightly, I'll make adjustments. So this first lecture means this lecture also, after this brief introduction, that's what we will start. We'll start with some basics of periodic sampling. The second lecture would be more about the relation. You have a continuous time domain in the beginning, you took a samples of it, okay? Then you have a discrete time domain, how the frequency spectrum of your discrete time domain is related to the frequency spectrum of your continuous time domain. That's something, those relationships we will discuss in the second lecture. And then suppose you did all the processing in the discrete time domain, okay? At the end of it, you have a discrete time signal that you have obtained as a result of your processing. Then you want to reconstruct a continuous time signal. So how do you do that? So that part, particularly for band limited signals, we would discuss in the third lecture. Then the next lecture would be you will connect all these modules put together, where you have a continuous time signal, you convert it into a discrete time, and then you are doing certain processing on it, and then at the end of that process you have a discrete time domain signal that you want to finally convert into a continuous time signal. So the whole pipeline we will be building, where you have both sampling followed by reconstruction and a DSP processing unit in between. Okay, now the fifth lecture would be about, suppose you have a discrete time signal itself, you are going to downsample that signal. Okay, when you are downsampling the signal, what would be the frequency spectrum of it, and how that would have an impact on the signal and other aspects. That's what you did. So downsampling by an integer value is what we would be discussing in the fifth lecture. Sixth lecture would be on suppose if you are upsampling a given discrete time signal, what would happen to the relationships of the frequency spectrum, aliasing, various other aspects we would be discussing there. And the last lecture of for sampling in this course is changing sampling rate. Suppose the fifth and sixth, when you have a either upsampling or downsampling by an integer value, then what happens if you are changing the sampling rate by a non-integer factor. So this is the tentative title, tentative modules within sampling that we are going to discuss this week. This week means this starting from this Monday, okay, till maybe next couple of weeks more. So roughly maybe 2 weeks or at most 3 weeks. This is the schedule for it. Okay, so let us now start with some basics of periodic sampling now. Okay, to this I'll work out things in the notepad in this notebook. So let me move to that mode. Okay, let me just adjust things here. Let me go to a notebook mode. Okay, hope you are able to see this. Okay, so discrete, what we are interested is in sampling also. Let me put it more specifically. Okay, what is of our interest is, for example, we are going to take a look at periodic sampling. This is of our interest for us, which means assume that you are applying a discrete time signal is obtained. This is obtained by periodic sampling of a continuous time signal, by periodic sampling of continuous time signal. This is what we are considering here, and then we will establish various things here. Okay, so for example, let me draw a sample signal here. This is BT. Okay, this is your continuous time signal, so let me call it as XC of T. What you are going to do now is you take samples of it periodically. So assume that this is your X of N. Now let's say you can periodically means at an interval of T you start taking the samples of it. So yeah, that should have been a straight line. Okay, too bad. So let me redraw that. Yeah, somewhat better. So this is your X of N plus 1. Okay, then with the same rate you take the things here. So this is your X of N plus 2, and you keep doing it at intervals of T. Okay, yeah, you keep drawing it that way. So this is how you are doing. So you are taking sample at after time T. Okay, so in other words, then I could say, yeah, let me change it to blue everything. Yeah, So your let's write something about this sampling frequency here, with which we are doing is we refer to it that sampling frequency as fs. This is equal to, now taking for every t seconds you are taking 1, so your sampling frequency is 1 by t samples per second. I could of course call the same thing as hertz also, correct? Now I could have mentioned it in omega also, sampling frequency, let me call it capital omega s, okay, which is nothing but 2 pi times fs, which is equal to 2 pi by t, units will be radians per second. This is what with which I am doing a sampling and thereby obtaining a discrete time signal. Okay, now let me give a mathematical or conceptual representation of this sampling. So let me write that first. So this is the first part, is how you are obtaining the signal. Okay, the second part, okay, we have a signal now, but for this to obtaining that signal we want to present a mathematical, or yeah, we want to give a mathematical or a conceptual representation of the process. Okay, representation of sampling is what we are going to do now. Okay, again this we are saying mathematical or conceptual mathematical representation of sampling. We are saying it's because in practice this is not the way you would be doing it, but this is what helps us to understand what happens to it when we are going through this process. Okay, let's start. Okay, so assume that you have initially a signal, continuous time signal is xc of t. Okay, and now you want to, out of this you want to create xs of t, which has values, still a continuous time signal, but has non-zero values at regular intervals only. To do that, what you need to do is you need to multiply it with an impulse train. Okay, you need to multiply it with, this is s of t is impulse train. Yeah, I know whatever I have talked so far might not be very clear to you, so let me write some things and then we will see it again. Okay, so when I say impulse train, okay, so how could you represent that? S of t, okay, small s of t is equal to n varying from minus infinity to plus infinity delta of t minus nt. Notice I am keeping here curly these kinds of brackets, meaning this is a continuous time signal. Okay, so how does that look like? This is a signal, right? You consider this as t, this as 0. Okay, I keep an arrow because that's a continuous time 1. Where will be the next one? For n equal to, for example, 1 t minus t. So you have the next one at t, the next one at 2t, okay, and so on up to infinity here. The same thing on the left hand side as well, minus t, minus 2t, and so on here. So that's your s of t. Okay, now what would happen when you multiply it with xc of t, which for example this one, So it essentially keeps values at around infinitesimally small area around 0 t, 2t, 3t, and so on, and of course on the negative side also. So that's a, you could think of it as a continuous time version of a discrete time signal as of now. Okay, that's what you could think of it, right? So then what you would like to do here is, let me move this a bit here, this name, so that I have some space here to draw something else. Okay, yeah, so here, for example, if I am doing integration over nt minus epsilon to nt plus epsilon dt, okay, this would be giving me x of n signal. That's the mathematical representation, right? So hope this is clear to you. Once you have that, in order to get x of n, you do that, you nt minus fc this xs of t. So that would be essentially keeping the retaining the xc of t values only at the multiples of 2t in the time axis. Okay, and then you integrate it over that nt minus fc around that point, so that you will get what you get there is x of n. Okay, so now let's write the expression for xs of t first here. Xs of t, we created it by multiplying xc of t with the impulse train. Notice here, it is telling you at what rate to take the samples of xc of t. That's what this impulse train. Okay, this is the impulse train, I mean, not the one which I have written there. Okay, this is telling you at what rate here. For example, it is telling you to take samples at a frequency of omega as radians per second. Then it is still in the continuous time domain. You integrate it over that period and then you get x of n, right? So if your t value is very large, it means 0 seconds, t seconds, 2t seconds, 3t seconds, that's where you are taking it. So you are taking samples very sparsely or at a larger intervals of time. Okay, so let's write the mathematical expression for this now. So this is equivalent to xc of t into summation of n varying from minus infinity to plus infinity delta of t minus nt, correct? Can I take this xc of t inside this? Anyway, there is no n here, so I could safely take without any problem. So I could write it as n is varying from minus infinity to plus infinity xc of t into delta of t minus nt. Hope you all remember the shifting property. So just a minute. Yeah, so hope you all remember the shifting property. This you could see will have value for t equal to nt only. It will have a value here because of this delta function, right? So I could in fact write this now as n equal to minus infinity to plus infinity. If I want, I could write it as xc of nt into delta of t minus nt. If I want, I could write it this way, correct? Okay, let me just quickly come back here to write the relationship between x of n and xc of t. Can you tell me that? If I want the n value, okay, how could I get that? That's nothing but xc of nt. Okay, notice here, assume that this is your t equal to 0. Of course you could have negative values also without loss of generality, but that's fine. You assume that this is your t equal to 0, so that gives you your x of 0. So x of 0 is xc of t, x of 1 is xc of t, okay, x of 0 is xc of 0, x of 1 is xc of t, x of 2 is xc of 2t, and so on. So this is an important relationship here. Okay, yeah, again we will come back here. So this is what you got, xs of t as xc of nt into delta of t minus nt. That's what I have written here. Okay, now what about your x of n now? Okay, if you are not already convinced that this operation would give you x of n, you call it with another variable, and at the end of the simplification you would see that this would be xc of nt. Okay, so this I could write it as nt minus epsilon to nt plus epsilon, okay, and xs of t dt, right? You take a look at here, xs of t into dt, that's x of n, depending on which n you want to compute, this is how it is. So this is nothing but nt minus epsilon to nt plus epsilon summation n varying from minus infinity to plus infinity. There is a conflict of variable name here, right? So let me write this variable now as k here, just to avoid the conflict with the n here already there. Okay, k varying from this, and then xc of, okay, let me for the time being I could write in fact even xc of t, of course this also would work out, into delta of t minus kt, t minus capital T here, sampling rate. Okay, this would give me xs of t, right, and integral with respect to t here, right? Okay, so this would be equivalent to what? Well, this kt, when this is equivalent to nt, that's only when you have this has a value. So I could get rid of this integration there and simply keep so this summation you are doing, yeah, sorry, I could get rid of the summation because your t is nt. There is only one possible value of k for which k, when k equal to n only, this delta is going to become 0. So there is, among that summation there is only one value, so I could simply write it as nt minus epsilon to nt plus epsilon xc of t, right, xc of t into delta of t minus, when k equal to n this would happen, into dt, right? And well, this I could further xc of t, this t varying, so this your t you are varying from nt minus epsilon to nt plus epsilon. If you notice, this is nothing but equivalent to xc of nt, xc of nt, which is nothing but of course x of n. So this, if I want, is nothing but of course x of n. Okay, was this clear? Why this has given us the way we have written this module as nt minus epsilon to nt epsilon? What is it that we are doing? Let's quickly recap it again. You have a continuous time signal, you want a sample version of it. When you multiply it with an impulse train, all you end up with is still a continuous time signal, but having only discrete values only around the integral multiples of t, and then from that you are again getting x of n by using integration or around that infinitesimal area around your value of nt. That's all, right? So then we got the expressions for xs of t. So far what we have got is, what's the, given that this is an impulse train, what's the expression for xs of t, and given xs of t, what is the expression for x of n. This is what we have done, right? Now what we do is, let's do a frequency domain representation of this xs of j omega. So in other words, suppose I know what's the frequency spectrum of xc of t, what will be knowing at which rate you are using this sample impulse train, what can you say, how does this frequency spectrum of xs of j omega, xs of t would look like? That's what we would like to do. So this is the third part we are going to do within this lecture, is frequency domain representation. Frequency domain representation of xs of j omega. This is what we are going to do now. Okay, right? So you have already seen xs of t is equivalent to, you get that sample version of continuous time signal by multiplying your x of t with an impulse train, right? Now as we are interested in the frequency spectrum, let me write it as xs of j omega. Okay, in the time domain, multiplication, in the Fourier domain is the continuous time signal, right? So this is equivalent to 1 by 2 pi into multiplication is equivalent in the frequency domain to convolution, xc of j omega convolved with s of j omega. What do we know about s of j omega? Do we already know it? What do we know is s of t, we know, for example, that's an impulse train n equal to minus infinity to plus infinity delta of t minus nt. So then this is a periodic impulse train. You should have done it in the signals and systems course. Hope you still remember that. This s of j omega would be equal to, impulse train would still will give you its Fourier transform is also impulse train, but now instead of t you would be having there 1 by t and with a multiplication factor of 2 pi by t. So what you get out of it is 2 pi by t, I am using here k instead of n, should have used, I could have used even n also, into delta of omega minus k times 2 pi by t. This is the impulse time. And of course this we have already have written in earlier, omega s is nothing but 2 pi by t, sampling frequency. This is what is telling you this impulse train, that's equivalent to 2 pi by t radians per second, correct? So I could write this as s of j omega is equal to 2 pi by t times summation k varying from minus infinity to plus infinity delta of omega minus k times omega s. This is your s of j omega. Okay, now let's go back to xs of, let's substitute it in the expression for frequency spectrum of xs of j omega. So that implies xs of j omega is equal to 1 by 2 pi, well here let me write the constant this out, 2 pi by t okay, into xc of j omega convolved with this summation of delta of omega minus k omega s. Okay, this 2 pi and this would get cancelled out. Okay, and then I have here j omega equal to, any idea on what this value would be, this convolution? uh, can I take the, so this convolution, if you remember, if I have an x of t, if I am convolving it with delta of t minus t naught, what I would get there, x of, this whole x of t would get shifted by that value. Okay, and then you are repeatedly doing it for varying values of k from minus infinity to plus infinity, so you have summation of all those terms. So what do you get here? This would be equivalent to k varying 1 by t is there outside, k varying from minus infinity to plus infinity, xc of j times omega minus k omega s, right? This is a very, very important result. Okay, xc of x, the frequency spectrum of a signal obtained as a result of multiplying a continuous time signal with an impulse time is also contains multiple copies of the, say, a summation of multiple copies of the frequency spectrum of the original signal, but each copy shifted by value of k for varying values of k from minus infinity to plus infinity. This is what this tells you. Okay, so the moment you got a discrete time version here, what's happening here is you are getting multiple copies of the frequency spectrum here. Okay, so maybe it would be more clear to you if I plot these results. So let me draw here, maybe as the next step here, let me do the plotting of x, the magnitude spectrum of j omega. Okay, so our assumption here throughout the sampling is, your assumption is that your xc of t is a band limited signal. So you could say beyond which frequencies it doesn't have any values, no other frequency exists beyond a particular threshold. So it's a band limited signal. X of t is a band limited signal. That's the assumption throughout. Okay, now which means, let me draw some signal here. Frequency signal, I am drawing frequency spectrum, so this has to be omega. It's a band limited. Okay, let this be the y-axis, let this signal be, yeah, I could have drawn any other shape as well, as long as it doesn't have any frequencies beyond a particular value. Let me call this maximum omega n. Let's assume it's a real signal, so which means it is symmetric over the y-axis. Okay, let's also take, without loss of generality, this magnitude being 1. Okay, and this is what the original, assume that the frequency spectrum of the original continuous time signal. Okay, now what is it that we were doing here? Now let's draw the frequency spectrum now of s of t. Okay, let's draw here the frequency spectrum for the impulse time. Okay, so this is your y-axis. Okay, delta of t minus nt summations it has. Okay, it has an impulse train at t equal to 0, and now we assume that it has a sampling of omega. It has, so where does the next value would be there for a given t? It will be there at, you take a look at here. The next one will be there at omega s. Okay, so let's take the omega s is somewhere here. Okay, omega s on this side somewhere here minus omega s, and of course this would go till infinity, this will go till infinity, 2 omega s. Okay, and so on, and here minus 2 omega s, and so on. This is for the magnitude spectrum of s of j omega. Okay, now what would be the convolutions of these two things? So let me draw that here, omega. Hope I managed to draw somewhat straight lines. Okay, and roughly 1 2 3 here. So what is it going to have? This is the expression. Yeah, this is going to get scaled by a value of 1 by t. That's the first thing. Okay, so let me draw it a different value now. Okay, and yeah, this value, if I assume the above one to be 1, this would be equal to, it's not writing there, yeah, because I folded the pen there. Okay. This value would be equal to 1 by t. Hope that's clear to you, because, okay, let me draw a line also here. This value is 1 by t because there is a multiplication factor of 1 by t. If this is 1, this would become 1 by t. If it is some a by t, it would have been. Okay, and what about this? Can you say something about what would be this value? Well, it is not changing anything there by scale there, so this should be at the same value as omega n, and this should be at minus omega n. But now it is placing copies at omega s, 2 omega s, 3 omega s, and so on, as well as minus omega s, minus 2 omega s, and minus 3 omega s, and so on. So I would get a copy here, one copy here, right? And assume that there is a, this is at omega s, assume there is a 2 omega s here. Again, around that place I would be getting another copy of it. Okay, shape will remain same. Okay, so here one copy here, and this would continue on both sides, and this is the magnitude of xs of j omega. Okay, now hope it's clear so far. Now is there any guarantee that the copies won't overlap with each other? Or when can you say, suppose if my omega s is small, okay, so let me draw one more diagram here where I have a smaller value of omega s. So this is my omega. Okay, instead of having this value of omega here, assume that I had omega s somewhere close here. Okay, somewhere, that means I played with this impulse train also. You need to try it a different impulse train. Okay, this would anyway, this shape will be there till omega n, but now your impulse train that t is large or omega s is small, what would happen then? You have copies like this, and same is the case on this side. So there is this your omega n, okay, this is your omega s, okay, and this is 0, okay, this center is again omega s, this is minus omega n minus omega s, and so on. So this effect of overlapping is referred to as aliasing. When your t is small enough, that means the rate at which you are taking samples, or in other words your omega s is large enough, there is no aliasing here. There is no aliasing in this case, for example, okay. We call it aliasing because at the same value you have two possible values for the same omega there, okay. That will corrupt the magnitude of frequencies there around that place. So when is there, so let me just add the final topic of this discussion, okay. Let me say that as aliasing. For a band limited signal, okay, the signal, the first thing is that you are considering a band limited signal. So this discussion is limited to band limited signals. Can you say from this diagram when there will not be any overlap? For that you try to write what this will be. See, this point is omega s, in that you subtract here omega n, this length is, so this would be equal to omega s minus omega n. So you could see here this omega s minus omega n is as long as this is greater than or equal to this omega n value here, there is no problem, correct? So this should be greater than or equal to omega n. That implies omega s should be greater than or equal to 2 times omega n. A very important result in sampling, the area of sampling, okay. This is Nyquist frequency or Nyquist rate at which you need to sample, it tells you. So what it tells you is, so this is again, after we go through it in more detail in the coming classes, it becomes clear. So far what you would say is, if this is satisfied, then there is no aliasing, and in the later classes you would see that if there is no aliasing, you could perfectly reconstruct the original continuous time signal from the samples that you have captured uniformly with a sampling rate of omega s, okay. So this is all for this class. In the next class we would see the about the frequency domain relationships between this x of n and xs of j omega, x of n and x of e power j omega, and xc of j omega. But yeah, carefully go through this. This is a very important. This forms the basis, okay, to understand the sampling process, okay. We'll stop here. We'll answer, if you have any questions here, I will answer those questions, okay, in the in your upcoming yeah, if you have any questions, I would answer them in the Zoom meeting. Before that, I would also post this, and along with the next video I will post for our discussion, okay. Hope you understood things. Go through them carefully before the next meeting, and see you. Thanks for watching. Yeah, if you have any questions, you could post them in the comments of this YouTube video as well, okay. See you in the next video. Thanks for watching.